Now that we know how to fit a classifier and use it to predict the labels of previously unseen data, we need to figure out how to measure its performance. That is, we need a metric. In classification problems, accuracy is a commonly used metric. The accuracy of a classifier is defined as the number of correct predictions divided by the total number of data points. This begs the question though, which data do we use to compute accuracy? Well, what we are really interested in is how well our model will perform on new data, that is, samples that the algorithm has never seen before. Well, you could compute the accuracy on the data you used to fit the classifier. However, as this data was used to train it, the classifier's performance will not be indicative of how well it can generalize to unseen data. For this reason, it's common practice to split your data into two sets, a training set and a test set. You train or fit the classifier on the training set, then you make predictions on the labeled test set and compare these predictions with the known labels. You then compute the accuracy of your predictions. To do this, we first import train test split from sklearn.model_selection. We then use the train test split function to randomly split our data. The first argument will be the feature data, the second, the targets or labels. The test size keyword argument specifies what proportion of the original data is used for the test set. Lastly, the random state quark sets a seed for the random number generator that splits the data into train and test. Setting the seed with the same argument later will allow you to reproduce the exact split and your downstream results. Train test split returns 4 arrays: the training data, the test data, the training labels, and the test labels. We unpack these into 4 variables: xtrain, xtest, ytrain, and ytest respectively. By default, train test split splits the data into 75% training data and 25% test data, which is a good rule of thumb. We specify the size of the test set using the keyword argument test size, which we do here to set it to 30%. It is also best practice to perform your split so that your split reflects the labels on your data. That is, you want the labels to be distributed in train and test sets as they are in the original data set. To achieve this, we use the keyword argument stratify equals y, where y is the list or array containing the labels. We then instantiate our k-nearest neighbors classifier, fit it to the training data using the fit method, make our predictions on the test data, and store the results as y_pred. Printing them shows that the predictions take on 3 values as expected. To check out the accuracy of our model, we use the score method of the model and pass it xtest and ytest. See here that the accuracy of our k-nearest neighbors model is approximately 95%, which is pretty good for an out-of-the-box model. Recall that we recently discussed the concept of a decision boundary. Here, we visualize a decision boundary for several increasing values of k in a KNN model. Note that, as k increases, the decision boundary gets smoother and less curvy. Therefore, we consider it to be a less complex model than those with lower k. Generally, complex models run the risk of being sensitive to noise in the specific data that you have, rather than reflecting general trends in the data. This is known as overfitting. If you increase k even more and make the model even simpler, then the model will perform less well on both test and training sets, as indicated in this schematic figure known as a model complexity curve. This is called underfitting. We can see that there is a sweet spot in the middle which gives us the best performance on the test set. Okay, now it's your turn to practice splitting your data, computing accuracy on your test set, and plotting model complexity curves.